Good evening. So today we will see questions that is from Welded plate girder. So we have what is maximum section and plastic section modulus. What is maximum section? So that is section means we have over here that is rolled section. So what is maximum rolled section available and what is the value of plastic section modulus for it? So this is maximum rolled section available. And then we have ISWB 600 at 1451 Newton per meter, and maximum plastic section modulus or plastic section modulus of this section is 4341.63 centimeter cube. So you can see this ISWB 141 point, that is kg per meter, generally multiply by 10, and this is my value of ZP 4341.63 centimeter cube when built-up beams are provided. So we are going to be with two criterias. That is when plastic section required greater than available. So if required is greater than 4341, then we have to go for built-up beams. Or when depth is restricted. So generally in case of landing, depth required is more, and we are going to restrict. That is depth of beam is restricted. I can mention specially depth of beam is restricted, and in that case also we are going for built-up beams. Then when plate girders are provided, so when span is large and loading is medium, or when span is small, load is large, means ultimately we can say when we have bending moment is very large. So bending moment is large, so we have to go for that is plate girder. Why are plate girders provided for large movement? Because in built-up beams, as we require ZP more, and if we will go with built-up beams, the number of plates required on your compression flange will increase. So if I will say, so my these plates, so required plate dimension will be very large, and due to this, my self weight of the section will increase, or self weight of the built up beam increases, and which is not economical uh, for this large moment, and therefore we are going to be with plate girders, because if we will see in plate girders we are going to provide these flange that is away from the neutral axis, and as we are going to provide it and away from the neutral axis, we are going to get increase in the moment of inertia, because we know we have formula that is I is equal to ICG plus A into H square. As you increase the distance of the flanges away from neutral axis, so your value of H increases, and which automatically increase value of I, and that is we have square, so it increases large, increases fast as your flange plates go away from the neutral axis. So you can see inertia increase square of the distance in one of the term, and that will increase your value of the moment of inertia, because ICG is very less compared with this A into H square. Then which components of plate girder resist shear and moment? So generally we have assumptions that flanges of girder resist bending moment and web resist shear. Which formula used for calculation of depth of web? Generally this is an empirical formula which is generally used to calculate the value of depth of the web, mk upon fy, that is 1 by 3, or cube root of mk upon fy. M is bending moment, k is d by tw, d we have depth of web, and tw is thickness of web, and this value of k again depends upon your stiffness provided. Then what is clause for this, that we will see. So what is formula for self weight? So generally this value is taken as 200 to 350. So for plate girders we are going to get this value, that is total load divided by 200, that is for your self weight of plate girder, I can say. For beams, we are generally 350. So built up beams, we have 250, 300. Likewise, we have to consider depending upon the load. What is formula for calculation of area of flanges? Now you can see. So we have, this will be neutral axis, and you can see this is my value of H. So if this value increases, then automatically my value of ZP also increases. So now you can see this. This is D by 2, which we are saying H. So ZP is AF into D by 2 into 2. So because we know ZP, we are going to take the moment of this area of flange, and that is about neutral axis. And as we are saying, flanges are going to resist moment, so we are going to neglect this web while calculating the value of ZP. Then we have ZP equal to AF into D. These two we have because we have this flange plate that is on both sides, and therefore we are considering this as twice. Then AF into D. Then MD upon gamma MO upon FY. So we know we have formula. If you will see formula, we have MD is equal to ZP FY upon gamma MO. And that we have modified. That is ZP is equal to MD gamma MO upon FY. And ZP we have AF into D. So AF we have MD gamma MO upon D into Fy. So using this formula, we are in position to calculate this value. And generally, we are going to consider this value, that is 0.3 into D, and then we will get this as BF, and accordingly we can calculate value of TF, that is thickness of flange, from this. Then what are the criteria for stiffness? This K value we have to consider to determine this value of D, that already we have seen. And this formula we have, that is cube root of MK upon Fy. And for this, whatever value we require, so cube root of mk upon f, and k we have to consider. If we do know, we have no stiffness, then my value of k is less than or equal to 67. So we have to consider d by tw between 0 to 67 in this case. If we have only vertical stiffness, then this value will be considered between 67 to 200. Generally this value is taken as 140, 150 likewise. Then if we have vertical stiffness along with transverse stiffness at 0.2d from top flange, then we are going to consider this value of k, that is d by tw between 200 to 250. If we have another horizontal stiffness which is at neutral axis, then that value is between 250 to 400. Now if we have value that is d by tw greater than or equal to 400, we have to change the dimensions. So considering these, we have to consider the value of k, and then we have to find value of d. Then what is criteria for width and thickness of flange plate? Just I have mentioned this 0.3d and tf. While providing this, we have to check it. This value should not be more than this, or I can write here, that is we have bf is equal to 16.8 tf, and by using this formula af is equal to bf into tf, and bf we have 16.8 into tf, and from this also you can find value of tf. And then we know we have bf as 16.8 tf, you can find bf, and then also you can provide this value. Now 8.4 we have, that is from table 2, bf upon tf, and from this we are going to get this plastic section 8.4. So these are the questions which are related with your plate girder. So we will today will stop here only. So thank you.